It's a great pleasure to be here. It's great to be back in Singapore. Back in 1995, I worked with Kavita Gandhi over there, who was a colleague of Edwin Q over here, to set up the first Clean Technology Information Center in Singapore with the Singapore Confederation of Industry. So it's a great pleasure to be back after all this time. So our company has developed a way to turn water into money. Who likes that? So what we have developed is a new way to extract energy from water that's moving and to turn it into power for either renewable energy or to move water out of canals for irrigation. So this technology is at the center of what we call the water energy nexus. And in this photograph here, you see this is one of our turbines in a canal. That canal is 90 miles long. We can put the turbines every couple hundred feet for 90 miles and string them together and make a lot of power from a lot of units together. The company actually grew out of a Tidal Power study, and if anybody's interested in ocean renewable energy, you can talk to me. I spent a year directing 8 engineering companies studying tidal power in Washington State. This is a large channel in the ocean there. The red color is fast currents. So we were looking at putting turbines in the ocean there to try to make power, and of course the conclusion was trying to do anything in the ocean is very, very expensive. If it was profitable, the oil companies would have figured it out already. So we started looking for places where the water is going fast, but we don't have all the problems that you have in the ocean. And what we found were the great canals of the world. So the world is now covered by huge canal systems and water systems that move water literally thousands of miles around. The canal on the lower left in this picture is in Argentina, and the upper right is a wastewater plant in Massachusetts, and the lower right is a canal in Washington State. They all have very similar characteristics though. First of all, these are not like rivers. These are controlled systems run by engineers. The water flow is totally predictable. They don't have very much debris. They don't have fish. They don't have people in them, we hope. And they are a predictable baseline power source because the water doesn't stop. It's not like wind and solar. The energy in this water doesn't turn off at nighttime. So it's baseline power. And the energy in the water is just like the energy in wind. We call it hydrokinetic energy. So it's the same physics. So what that means is, just like in wind, if you double the speed of the wind or the water, you get 8 times as much power out of it. The power is a cube function, okay? So if you go twice as fast, you get 8 times as much energy. So fast water, just like fast wind, is what we want. And what we have is a world of canals where there are lots of places where the water goes really fast. So our concern was how to get this energy out of it. And if you look at the canal on the lower left, the only way to do this in the past was to build some kind of a big paddle wheel over the surface. And that meant putting a huge structure, like a surface wheel, like the one you have here in Singapore, for example, over it, and it just never paid off because it just didn't make enough power. Now, how many of these canals are out there? Well, what's really surprising is that there's literally over 1 million miles of large canals in the world that are now lined with concrete, run by engineers, and have predictable power sources. Here we see 2 canals from India. On the left-hand side is the Chile Canal, and that canal is about 11 miles long. Our first customer and investor has bought 3 of our turbines, and they have given us a letter of intent to put 400 turbines into that one canal in an 11-kilometer stretch. On the right-hand side is another one of the great canals crossing the Punjab province. They have 4,000 kilometers of big canals just in the Punjab area, and I'll be there next week, so if anybody's interested in talking about India, we'd love to know about it. We'll be there, sponsored by the International Finance Corporation in a project to work with the government of Punjab. So the point is that this is a global resource that operates all over the planet. And here on this map, I've drawn circles around the areas of the world that have massive irrigation systems. The western United States, where we live, is one of the major areas. I'll spend some time on that. Areas that you might not have thought of. The west coast of South America is now being massively irrigated for sugarcane. Argentina and Paraguay, massive systems there. Central Asia. Europe, of course, for many areas. China is a massive area. We have already been in partnership, we're already in partnership with a research institute in China. You might have heard my question about that yesterday. They have canals in large quantities. Southeast Australia has massive systems, and even South Africa. So around the world, you can see why there's millions of miles of canals and at least 1 million miles of big canals. And the great thing about a canal is a canal is a canal. They're all the same. it's a big concrete lined ditch. And that means if you make a machine that works in one ditch, it'll work in all the ditches. So our turbines are designed to be fully submerged in the canal. They're like underwater paddle wheels. And we have two types. One is for flat flows, like on the one on the left, and then we also have a waterfall turbine on the right so that's able to extract power from the sun drops. They all share the same things in common. First of all, you have to do very, very little preparation. These turbines can be installed with 2 ropes in an hour. Try saying you can do hydropower in an hour. No one's ever been able to say that, ever. There's very little permitting because there's no environment. There's no fish, there's no birds, there's nothing in these canals. We don't have any environmental issues in these canals. So it's environmentally sustainable, it's modular and scalable, and it's also very reliable, as I said, because the water's predictable. They can tell you that on August 15th at 10 a.m. the power there will be X. And it's run by an engineer. They've got the data to prove it. So the value proposition we're working on is first of all based on electricity generation. And our turbines are able to produce power at a rate of about $4,000 per kilowatt installed. That's the installation cost. Okay? And that's fully installed. And then on a 20-year lifetime for the machinery, a level cost of energy of 4 to 6 cents a kilowatt. We have a low cost of energy because this runs all the time. It doesn't stop running in the middle of the night or when it's not windy. So in the United States, we have a pretty 6-year payback in a market where the cost of energy is about 11 cents a kilowatt. But in areas where the cost of power is much higher, the payback, of course, is much faster. In remote areas where the power cost might be as much as 80 cents a kilowatt, a payback that we can show of about a year. So the faster the water goes, the more power you make. And the farther away you are, the more valuable the power is. So the payback increases. So our initial market opportunity for these machines is in the canals in the western United States. There are over 47,000 miles of canals that are operated by the federal government. We have the only license granted in the United States to put turbines in canals from the federal government. And they're our first demonstration site, as I'll show you in a minute. And you can see from the numbers here that out of 47,000 miles, at 10 turbines per mile with a penetration rate of 10%, that comes out to about 47,000 units. And at $20,000 a machine, that's about a $950 million opportunity there. And then that's just in the western United States. That's just one of those circles on the map, remember? On the waterfall side, we're targeted to the northeast USA because they have lots and lots of wastewater treatment plants and a lot of vertical altitude, so lots of drops, and we see a market there based on estimates by consulting engineers who work in that sector of about a $16 million market there. So what is our product? It's a floating turbine. And it can make from 50 watts to 10 kilowatts. Basically, you have a rotor in between 2 end pieces. We call them the end caps, the yellow end pieces there. Generators or pumps are located inside those end pieces. And they either make power or they pump water. And it just floats and it's attached to the shore with 2 ropes. And the power goes up the cable, up to the shore. And it can be used right there. So that's why it's easy to get into the water and cheap, because you don't have to do any construction. And it's modular and scalable. Our intention is to make them not bigger than about 7 feet in diameter and 18 feet long, because then we can put them in a shipping container and we can nail a turbine to somebody anywhere in the world. So one of the innovations we have is a new type of turbine rotor. This is called our flip wing turbine rotor, and it's made out of flat pieces of metal. As you can see, what happens is you have a shaft in the center and then a disc at either end. You're looking at it end on. The blades are hinged on the outside, and they're just long enough to reach that inside shaft. So that inside piece catches the blade, and then the water pushes it across. It has some neat advantages. Number one, it's easy and cheap to make. This is a third world turbine because you can make it out of sheet metal. You can't make a propeller in a village, but you can make this turbine in a village. It's almost impossible to foul it with debris because it's self-clearing. When things get on the blades, as it goes around and spins, it tosses the weeds and things off the back. We ran this for 2 months in a canal and it never got fouled once, even though there was lots of weeds and bags in the canal. And because it's flat squares, it can be scaled up or scaled down very easily, so you can cut it to fit very simply. Now that is one of the rotors we've used, but we discovered after a while that we could put other rotors on it as well that makes the machine more adaptable to other types of situations. So we have a high-speed channel turbine, We have one for spillways and waterfalls. We have a different version for slow and steady channels, and the lower right is our flip wing one that adapts to all these situations. So we call it a switchblade turbine, and the key to the business of production here is that by making one central chassis, which is the shaft and the generators, we can now make it adaptable to almost any type of water situation, which means that we can mass produce the main component and drive the cost down. So the small machine is designed to power batteries, okay, or village level power, up to 1 kilowatt. So it was designed originally to meet the US Navy's goal of 24 amps by 24 volts, 2-car batteries in sequence, and to be man portable, and we did it for them. This is the US Navy's demonstration of the turbine last September, and we're now working with the Navy on further versions of this. They want a military portable version of it. And this is now this is a show, it's operating in a flow of 1.5 meters per second. It's making 500 watts. The Canal turbine mill-size one is designed to produce up to 9 kilowatts, and this is a little demonstration from last year, from 2010. The truck shows up with the turbine, the crane picks it up, it lowers into the water, it's tied to the bridge, and it's installed in 5 hours. And it can come out of the water very quickly as well. So now that canal, again, is a 90-mile long canal, and we can do this every couple of 100 feet, and we can do it quickly. So here's an example of the canal in a flume, and this is an interesting application, a good demonstration of how this works, because the turbines can be made rectangular to fit very tightly in a channel. That means the efficiency goes up, because all the water has to go through the turbine. But also, you'll see from this, the turbine actually acts like a little dam, and you can control the height of the water in the canal by operating the turbine. The faster the turbine goes, the more water it lets through it. The slower it goes, the more it acts like a dam. So you can actually use the turbine. In many canals, you see little places where the water is dropped down, and those are just little dams. But we can turn each one of those into a power source now. And you can see it, there it is, it's working. So our new turbine, and by the way, we're our Autodesk people. Anybody here from Autodesk? This is one of our Autodesk renditions. And this is the new machine. And here you can see it being tested last month on the river. And this is the fast, high-speed blade, so this is suitable for a fast flow that's very laminar. The big size turbine here you see, you get a sense for the scale of it. There I am with my chief engineer, and we towed this back and forth on the rivers. Here it is being installed in a large canal in Washington State. Again, this is that's that 90-mile canal I was telling you about. And these are big waterways. These are like highways of water. And so you can get a sense for the scale of that. That thing goes for 90 miles. So here's the crane putting it in, and there's the splashdown. This was in March. And making power. Now this was rated at 5 kilowatts power, but in the canal it made 8 kilowatts because it's blocking a lot of the canal. So we actually made more power than we expected with this. This is sponsored by the federal government. Now the waterfall turbine was designed initially for spillways, but we found out that wastewater plants can use it. So here it is installed in the clean end of a wastewater plant. The water is being pushed down one side of the waterfall into the turbine. This is an example of a good site. That's a wastewater plant pouring contact tanks. We can put about 12 turbines along that rim. And again, the same concept of portability is critical. It's fast and drops in quickly. And so they don't have to do any construction, and they can use the power themselves. And this is a picture of what the new turbine is going to be like. This will be installed in a water plant in California in 2 months, and it'll make about 25 kilowatts. So why is this working? Why is this? It seems like an easy idea, but why didn't people do it in the past? And the reason is because of 2 enabling components. One is the generators. Now we have new generators that run at low speed. We don't have to be at 1800 RPM. We can use permanent magnet direct drive generators that didn't exist in the 20th century. And we can now get them, in fact, from washing machines. Our small turbines, we use Whirlpool washing machine motors run backwards. And we can get them for free from old washing machines. I'm a recycler, you can see. And we also have the ability to convert the power into useful grid-type power now with the new inverters. And the other part of it is our business model, which is to focus on artificial water channels only. Don't put them in rivers. Don't put them in the ocean. Don't try to go and climb a mountain and hang it in the jungle. Stay in these big canals because it enables you to get to scale quickly. So our competition, of course, is other sources of power. The customer wants electricity, and so we have to compete against diesel or solar or wind or dams. Our advantages are that the cost is low. It's very easy. It's much easier than any other type of thing to do. We can drop it in an hour. It's very reliable because the water never stops. It's predictable, and it's very clean, of course, and finally it's safe. Because the turbines spin slower than the water speed itself, remember it's resisting the water, even if there is a fish or a person in the water, it's like going against the wall. It's not like a blade that will spin and hit you and cut you, so it's safe. There are a few other companies making turbines that are targeted primarily to rivers and to the ocean. So on the right side you see the new energy turbine. It's a vertical axis design. It's more expensive. It's less adaptable. And there's some other companies making turbines for rivers and the ocean, but they just have a very hard time. What they're doing is they're spending all of their investors' money on demonstration projects and then going broke. So our sustainable advantage is that, first of all, we are the first mover. There is nobody else in the world doing this yet. And so we're working very fast to outrun the competition. We have great engineering development and great market development, and we also have funding. We've already raised money from Series A round. We have 40 investors. And we also have strong IP, and we have strong partnerships. As I said, we have the only license from the U.S. federal government to do this. We're looking to partner with governments elsewhere. We have great oceanographic and technology people working with us, the Woodsville Oceanographic Institution. And just last month, we signed 2 contracts with 2 universities, California State University and Central Washington University, and they're designing components for our turbines, and we will own the IP, which is very unusual if anybody knows about doing contracts with universities. We will license the IP back to the university for their R&D. And of course, I've got a background in international development, so we have a very good ability to understand what we're getting into. So the expansion markets around the world are canals, thermal power plant discharges, wastewater discharges, and water purification. The mining industry is one of great potential because mining sites usually have to build their own rivers and their own drainage systems, and they don't mind about chopping up the world because they're already doing it. And even pipelines. We have a design for turbines and pipelines. We're focused on canals, but there's a number of related things. Now, Andrew Chung earlier was talking about disruption. What does this mean? It means that canals are usually, and always have been, designed to move water slowly because erosion is bad for it. But now they're lining the canals with concrete to reduce the seepage, losing water from soaking into the ground. But if you're lining the canal with concrete, you don't have an erosion problem anymore. So now you can make the canal narrow and fast. Remember, if you narrow that canal down, the water will speed up. And now you can get a lot more power out of it. So you see a big slow canal on the top, and on the left-hand side you see another canal. Much, much faster, same volume of water, but much narrower. What this means is that we're going to be working with the civil engineering companies and the development organizations to change the way canals are designed. It's not about just moving water anymore. It's about moving water and making money in the process. And this is going to rewrite the textbooks on civil engineering for water infrastructure. They didn't have the technology in the past, now they do. So this is going to have great impact. It's going to create new local economies. You can now put power sources for hundreds of miles out in rural areas. You can pump water out of the canals to irrigate the land on either side. How much is thousands of miles of new farmland worth? We don't know. We can't put it in our business plan because I can't quantify it. But you know it's worth a lot. And it's also a new industrial sector because this is going to be like making cars. These are highways of water, and we're inventing something very similar to a car. And we're going to make a lot of them. We've got a lot of recognition for our organization. We've been winning great contests. For those of you who are investors that are concerned about business models, we have won 3 international business plan competitions judged by VCs. They invited me to Singapore for International Water Week, and that's why that's what inspired me to come in the first place. So I'll be at Singapore International Water Week starting on Sunday, and we've been recognized by a lot of others as well. We have a great team, my own background in international development. We have very serious engineers on board, both with university backgrounds and also heavy industry. And we have 40 Series A investors, and many of them are quite strategic. They're very actively helping us. We expect the company to grow fast because once, as I said, one turbine in a canal is just like another turbine, and there's 1 million miles of canals. So once it works, and we already showed you it works, it's going to go fast. So we raised $2.5 million already from our Series A. We're looking to raise $5 million in the Series B. We're already receiving some term sheets, but I'm very interested in having investors from Asia because of obviously the market here. We'll use the money to install turbines and test them out, and we're also eligible for a lot of non-dilutive funding from grants, because many people are giving grants for this. And our objective eventually is that this company will be sold, and we're already in discussion with Siemens, Suez, Veolia, and EDF, and they're all interested in trying this out. So we're changing the water energy game. The water energy nexus is at Hydrovolts, and we look forward to talking to you. Thank you very much.
All right.